Hello everyone. We are giving statics lectures. Our topic, Newton's laws. We will examine Newtonian mechanics in these lectures. So we will solve problems according to Newton's principles. So let's remember Newton's laws. First, the principle that we will use most in statics is the principle of inertia. What does the principle of inertia say? An object remains at rest or makes uniform rectilinear motion if no unbalanced force acts on it. If an object is at rest, then the sum of the forces acting on that object is zero. Or we can say the opposite. Both are valid. If the sum of the forces acting on an object is zero, that object remains stationary, or if it was moving, if it has a predetermined velocity, it makes uniform rectilinear motion. In statics, objects are usually stationary. But even if it is moving, if the resultant of the forces acting on that object is zero, we can examine it statically. Newton's second law. The acceleration of an object is directly proportional to the resultant force acting on it and is in the same direction. It is inversely proportional to its mass. We can express this relation as follows. Total force equals mass times acceleration. Total F equals ma. This is a vector equation. Therefore, the directions of the vector on the left and the vector on the right are equal to each other as well as their magnitude. The third principle. The principle of interaction. The forces between two bodies that exert forces on each other are called interaction forces. We are talking about two forces. We call these two forces the interaction force pair. These forces are of equal magnitude, opposite direction, and in the same line of action. If we examine the figure, let's assume that the body A and B exert forces by contacting each other. The force A exerts on B is of equal magnitude and opposite direction to the force B exerts on A. It is on the same line of action. Newton's third law, when talking about the interaction force pair between two bodies that exert a force on each other, means that each force has a counterpart on the object that exerts the force. Now let's take an example. Consider such a truss. Let it be loaded with two loads and supported by two supports. If we draw the free body diagram, show the support reactions, we get a figure like this. The own weights of trusses are often neglected. They are neglected because they are small compared to the loads they carry. We do not show it here. Let us now examine these forces. For example, the force exerted by the support A on the truss has a counterpart on the support A. The truss also exerts a force on the support A. These two forces are interaction force pair. The same is true for the support B. The force exerted by the support B on the truss also has its counterpart on the support B. These two forces are in opposite directions with equal magnitude. It is on the same line of action. These are also called interaction force pair. Let's look at the loads. The force P has a counterpart on the body that exerts the force P. These two form an interaction force pair. Likewise, the force F has a counterpart on the object that applies the force F to the truss. These two forces form an interaction force pair. Newton's third law is often referred to in the literature as the action-reaction principle. But calling it the action-reaction principle can cause some confusion. For example, in this truss, the loads applied to the truss are the action forces. Support reactions are reaction forces. Action forces are the forces that cause reaction forces to arise. When we remove the effects, the reactions also disappear. These forces do not form an interaction force pair. Let's examine the gravitational force. For example, let's consider the Earth and the Moon. They exert a gravitational force on each other. These gravitational forces are the interaction force pair. But they are not action-reaction. Because one of these forces is not the force that causes the other to be arise. Both of these forces are action forces. Let's go back to the truss again. If we examine the support reactions a little more, we said that these forces are interaction force pair, we also see that they are action-reaction. The truss applies an action force to the support A, and the support reacts to it. It exerts a force of equal magnitude in the opposite direction. So is the support B. These force pairs are both action-reaction and interaction force pair. In fact, the reason why this principle is called the action-reaction principle in the literature is because some forces are interaction force pair and also action-reaction. However, there are forces that are not interaction force pair although that are action-reaction, and there are forces that are not an action-reaction even though they are an interaction force pair. As we have mentioned before, let's move on to Newton's law of gravitation. Objects in space exert gravitational force on each other. The magnitude of the gravitational force between any two objects is found by the following relation. In this relation, K is the universal gravitational constant. It has a certain value. We gave it that way. m1 and m2 are the masses of the objects. What is mass? The amount of matter an object has is called mass. R is the distance between them, between the centers of mass. Force is inversely proportional to R squared. Let's talk about weight. The gravitational force exerted by the Earth on any object is called weight. Let's consider an object at or near the Earth's surface. In the equation where we find the gravitational force, let m1 be the mass of the Earth and m2 be the mass of the other object near the Earth's surface. R is the distance between the center of mass of the Earth and the center of mass of the object. Of course, since the radius of the object or the dimensions of the object are unimportant respect to the radius of the Earth, we can take R as the radius of the Earth. The weight is equal to this value. The weight is denoted by the letter W, K times m1 over R squared is a constant. For the Earth, for the objects around the Earth. Therefore, instead of doing that multiplication every time, we do it once and use it all the time. We call this the gravitational coefficient. We get a coefficient from here, we denote it with G. We call it the gravitational coefficient. We find the weight by multiplying with whatever the mass of the object is. We write it as W equals mg. We take G to the end, not the beginning. To simulate Newton's second law. Now, let us remind you that the weight force is always directed vertically and downwards. Let's examine the figure on the right. Let this object be an object that moves only under the influence of gravity. No other force acts. So the acceleration of this object is equal to g. So the acceleration due to gravity is equal to g. It is equal to the gravitational coefficient. What is the value of g? We can accept the value of g as 9.81 for Turkey. In these lectures, the value of g will be taken as 9.81 meters per second squared. In practical calculations g equals 10 can be taken. In mind calculations, in practice, we can take g as 10 in the calculations to get a preliminary idea. But in normal calculations, it is not correct to take g as 10. G should be 9.81 meters per second squared. We calculate with a calculator, with a computer. Then why take g as 10? However, when calculating in mind, for example in test exams, g can be taken as 10. But g should not be taken as 10 in exams made with a calculator. Let's talk about the units to be used in these lectures. In these lectures, we will use SI units. What are SI units? Let's have a look at them. The unit of mass is kilogram, for short kg symbol, the unit of length is meter, we will denote it with the letter m. The unit of time is second, we will denote it with the letter s. Unit of force, of course, in this lesson, our job will be to deal with forces. Therefore, the unit of force is important to us. We're going to show it with Newton. We'll denote it with the letter N symbol. Apart from these, we will also have a moment quantity. It will have units of force times length, that is, Newton meters. 3 of these units are basic units. 3 of the units we will use in these lectures, namely mass, length and time units, are the basic units. The unit of force, N, is a derived unit. 1 Newton equals 1 kilogram meter per second squared. We will call it Newton for short. We will also use the unit prefixes, because the number of digits we get can be very large. In order to reduce the number of digits to reasonable levels, we will use these prefixes to reduce them to 3 to 4 digits. Let's see what they are. Giga is 10 to the power of 9, its symbol is G, mega is 10 to the power of 6, its symbol is M, kilo is 10 cubed, its symbol is K, milli is 10 to the power of -3, its symbol is M. We said above that we will use the kilogram as the unit of mass. If we pay attention, there is kilo in front of it. In fact, the unit of mass is gram. But since the gram is small, we take the kilogram as the basic unit. We will. Kilo is a number. It doesn't matter which unit comes after it. It can come in front of the meter as well. It can come in the front of Newton or second. That's 1,000 times that. For example, kilometer means 1,000 meters, kilonewton means 1,000 newtons. Mega can come before gram, for example, megagram. Megagram instead of kilogram. Megagram is 10 to the power of 6 gram or 1,000 kilograms. 1 megagram is 1,000 kilograms. There is a non-standard unit, in mass, ton. 1,000 kilograms equal to 1 ton. We will not use it. Although we do, it's rare. Goodbye.